So today's lecture was about hydrodynamic interpretation of the diffusivity, where a particle A in a solution B. So if you think of this particle in some sort of solvent and is moving, we need some sort of driving force, and that could be pressure, temperature, or concentration gradient, and it could be electrical, magnetic, etc. So in the case where the Reynolds number is really low, approaching like 0, we call it creep flow. And in such case, we can see we have this force, we call it chemical, into z direction, and then we have opposing force, which is a drag force, opposing the chemical force. And we're going to assume that the particle velocity is constant here. So the chemical potential gradient is what really driving the this is the driving force of this mass transfer, and that could be described as this thing equal g over delta ni, and ni is what it is representing is the number of molecule, the I molecule, and the g is the Gibbs free energy. So what this really is a potential molar Gibbs free energy. And this chemical potential driving force is the driving force, but we will commonly think of it as the concentration gradient as the driving force. And that is true, because the negative of gradient, so negative gradient is the driving force, just like in fluid flow, how the pressure goes from high to low, and they increase in z direction, so they have the negative sign. But I went kind of tangent. So going back to this chemical potential gradient, we have this Fc, which is C represent chemical, and so this chemical force, potential force, and the drag force are same. And in such case, we show that this is d mu over dz, negative d mu over dz equal 3 pi, and this is times viscosity times drift velocity times particle diameter. And it makes sense for the drag force to have this particle diameter, drift velocity, and viscosity. As they increases, their drag forces increase as well. And continuing on, we have this same. We can also represent the force of drag with the velocity times the frictional coefficient. And if we do so, we combine with the previous equation, we get this Fc, the chemical force times drag force, is equal to negative d mu over dz equal the particle velocity times frictional coefficient, or ui times lij. And we can further enhance this equation, where this to RT over CI. C is the concentration of I, and then 1 plus CI mu ln this gamma I, and gamma I is an activity coefficient, which really shows how ideal the solution is. And what they mean by ideal is for gas, ideal gas doesn't have intermolecular interaction, where liquid, it has to be present, right? So what they are trying to say with the ideal solution is all intermolecular interactions are same. So the particle A's and particle A's, A and A's interaction is equal to particle B and B's, which is also equal to particle A and B. For water, it would be hydrogen, oxygen, and hydrogen. So in ideal case, the gamma will be 1, and in the worst case, it will approach 0. But in such, we're going to assume that this ideal solution and the gamma is 1, and at ln1 it becomes 0, so this term disappears, and this is just 1, and then 1 times other stuff is just other stuff, so this whole thing disappears, and we can narrow it down to this u, and then we solve this equation. So negative RT times over concentration times this concentration difference gradient is equal to this U times Li, which is a friction coefficient. So this is a drag force. I think we are talking here, and then if you multiply by the Ci in both cases, concentration in both cases, this becomes a flux. And then if we move this Li over here, we get this term. So flux is equal to negative RT over frictional coefficient times the concentration gradient. And in the general case, we can define the diffusivity of Ij as the negative RT over Lij, where L is the frictional coefficient, and that's applicable for mesoscopic objects such as the objects that are in 2 to 50 nanometer size. But in specific cases where there are very low Reynolds number, like in our body, we use this Stokes law limit equation, which is a kT, where k is the Boltzmann constant, over 3 pi viscosity times dp. What is dp? I gotta figure that out. So all along we were talking about this ideal solution cases, but for non-ideal cases where the gamma is not equal to 1, we have to do something different. And we have this delta with d with this line going across it, and that is 1 over frictional coefficient. And that kind of makes sense where if the lower the diffusivity, lower the frictional coefficient, the higher the diffusivity, right? But that isn't really work out pretty like that, but we'll continue. So now in the non-ideal cases, we show as this this line d times RT was the same thing over beforehand, but we have this Xi, which is a mole fraction, which is a ratio of solute and solvent. And we can see that gamma and X have negative correlation, which makes sense because as there are more of the if the ratio is really low, that means there's a very little solute, and then the intermolecular interactions difference will be pretty low, and hence the higher the gamma I. But as the mole fraction increases, that means there are more solute in the solvent, and then it behaves more like non-ideal solutions, hence the negative correlation between the gamma and the mole fraction Xi. So we are here violating Fick's first law, which says that the concentration gradient is the driving force of the mass transfer by 2 ways. One is that the diffusivity is correlated to concentration, and the second one is the concentration gradient is not the driving force, and the real driving force is the chemical potential. And what some people do is they opted to Fick's first law and replace the concentration gradient with the chemical potential to more accurately model the mass transfer phenomena. So far we have said that Dij, the diffusivity of I in J solution and the diffusivity of J in I solutions are not the same. But what about the frictional coefficient Lij and Lji? Well, they are actually indeed the same. So how could that be the case, right? So that's because of the concentration differences we have. And so we know that the concentration matters really. So going deeper into concentrations, so we have Dij with a concentration of I, and in this ideal cases, we have this equation going on where diffusivity times this viscosity, and then this D with the D circle, so it's infinitely dilute, and that all over the viscosity of the mixture. But in most liquid, the viscosities are pretty similar they differ by maybe twice, twofold, but diffusivity, it could differ by many order of magnitudes. So the difference is pretty insignificant, and if we can simplify this equation to be just diffusivity of Ij times Xj times Dji to the power of Xi. And this is called the Vignes correlation. I probably butchered the pronunciation. And for the non-ideal, we were talking about ideal cases here, but for non-ideal cases of the diffusivity where it has a concentration term as one of the components, we have this the line Dij times RT 1 plus delta ln gamma xi over gamma x times xi.